Okay, the question reads was like this. A ball swings counterclockwise in a vertical circle. It's a circular motion. I hope you can hear me. And at the end of a rope, which is 1.5 meters long, so the radius of the circular motion is given as 1.5. It's a vertical circle. Let's draw the picture of the problem. This is the orbit of the motion. It's a circle. This is the center. At one point, the ball is, I think this is the vertical line. Let me first draw the vertical line. Yeah, like you can take this as a y-axis. This is the center. When the ball is 36.9 degrees past the lowest point on its way up, it goes in a counterclockwise direction. Counterclockwise direction is this direction. So it is somewhere over here. This is the rope sting. Rope. Yeah, this is the rope. And this is the object. And this angle is given as 36.9 degrees. Okay. All right, right over here, it says the total acceleration is given. Acceleration of, you just take this is a y-axis, this is the x-axis. The acceleration at this point is given as minus 22.5 I plus 20.2 J, okay? And obviously the object has some mass M, let's say, put the mass over here. And, right at this position, for these kind of questions, the first thing you have to do is that what are the forces on the particle? The one is that this rope have a tension force, this is T, right toward the center. And the other is that the object is having weight, which is mg, under two force. So T is in this direction, this is T force, and this is M. So the particle is going in this direction, is moving in this direction. Okay, this is not a force. There are two forces. Let me put this over here. This is the one force T and the other force, which is mg. And you can resolve this, you know that this is going to be the angle. The angle is over here. This is 90 minus 36.9, etc. You know the angles also. You know the angle of the T making with the horizontal, or let's erase this one. Let's put this angle over here. This is the vertical line. Yeah, this is the angle, which is 36.9 degrees. And mg is right down on the vertical axis. T is toward this direction, and the angle is given. Sketch a vector diagram showing the components of its acceleration. And the acceleration is, if we want to sketch a diagram, this is the object, M. The acceleration vector is pointing in this direction, AX. This is the component minus 22.5. And the other component, the vertical component, is up. Sorry. The vertical component is up. This is AX and this is AY. AX is minus 22.5 and AY is 22.2. So this is the acceleration vector. Of course, it's going to be sum of these two components. So this is your acceleration vector. This A is over here. This is A. Okay. Determine the magnitude of its radial acceleration. The radial acceleration. So yeah, that's a good point. What is the radial acceleration? The radial acceleration is along this line, along the t vector, okay? T tension force. So in order to find the radial component of the acceleration, right, we have to resolve these components on this line, okay? One thing is that what is this radial acceleration is related to? The radial acceleration is this is the total acceleration, all right? The total acceleration vector, and this is, let's say, let's draw also the tangent line. This is the tangent line. The tangent line, the circle goes like this, okay? And this is the tangent line, and the one thing that you can do is, well, if you can find the velocity right at that point, you know the acceleration, but you don't know velocity. So the radial acceleration is going to be related to velocity vector, as this is the radial acceleration or centripetal acceleration. Velocity squared divided by r. And r is the length of this rope, okay? It is given in the problem, 1.5 meters. So do we know v? But we don't know v. What we know that the total acceleration, right? And the total acceleration has components ax, ay, and the tangential acceleration is going to be just projection of these ay and ax on this line, okay? Well, on this line, we know also that this line is this line, in fact. This is the line over here. We can resolve it. We can resolve this total acceleration in the direction of this radial direction. But let's calculate first what t is. Can we find what t is? Okay, if you just draw this line that is toward the center, this is the line that goes toward the center. We also know that this mg force is making an angle with the same angle with that of t, which is 36.9. Okay, and what is this line? This line is in fact the centripetal line. Okay, and the centripetal line, to find this to find the total the centripetal acceleration, we need to find the total force along the centripetal line. The total force along the centripetal line is going to be, the ball has no given mass. Mass time it's AC, right? Mass time AC. And the centripetal line, you have this force T minus mg times cosine of this 36.9, whatever it is. Cosine, let's give this as a theta. All right? Because toward the center, we take the forces as to be positive. So mg is going to have a component which is out of the center. It goes like this. And that component is mg cosine theta. This is going to be m times AC, which is centripetal acceleration. Or radial acceleration. Okay, this is because the problem is in part B is asking of the radial acceleration. This is the radial acceleration. But the thing is, we don't know what m is. We don't know what t is, right? And all we know, in fact, we know this total acceleration. From that total acceleration vector, we may not need this equation to find the radial acceleration. Okay, because these are the components. We know the components, so this is the total acceleration vector, but this total acceleration vector does not mean that this line does not mean that it's going toward the center. This is the acceleration vector, okay? The acceleration vector is having an angle with the horizontal. Let's find the angle of the acceleration vector with the horizontal. This is, let's say, alpha. This angle is alpha. It is not necessarily equal to, well, let's not choose this alpha, but choose this alpha, okay? This alpha angle, this angle is not necessarily equal to this angle, which is 36.9 degrees. But we can find anyway, we can find what this alpha is. This tangent of alpha, or alpha, is equal to arctangent. The one that sees this angle right over here is AX, right? It is AX divided by AY. So we can find this angle alpha through this numbers. AX, I'm going to take the positive part because, you know, I take this length as positive, which is arctangent 22.5 divided by AY is 20.2. So this will give you the angle alpha, right? And the angle alpha is this one, angle alpha, and the angle 36.9 may not be necessarily the same, but we take this theta, this is theta, which is 36.5, this is alpha. Theta minus alpha is going to be the angle between this acceleration vector and the centripetal line. Okay? And the centripetal acceleration is going to be, it is a little bit, becomes complicated solution, but anyway, I hope you can follow it. This angle, cosine of this angle is going to be multiplied by this acceleration vector magnitude to find the acceleration in the radial direction. Let me put it over here. AC is going to be the acceleration vector magnitude, which is AX squared plus AY squared in square root multiplied by cosine theta minus alpha. Well, theta minus alpha, as I said, theta is 36.1, the theta is, you know, but alpha is going to be found from this equation. Once you find this angle alpha, you put it over here, take the cosine of the difference, and multiply by square root of AX squared plus AY squared to find the acceleration vector along the radial direction, which is this one. It's a little bit complicated, but, you know, that's how it goes. Well, of course, after finding the radial acceleration, finding the velocity for part C is easy because you know what this is, you know what R is 1.5 given in the problem. V is going to be just, let me put over here, V is going to be R times AC, which is this one you calculated from here, in square root, meter per second. Arctangent neden aldık? Şurada. Arctangent almamızın sebebi şu vektör A vektörü, yani toplam ivme vektörünün dikey eksenle, yani bu eksenle yaptığı açıyı bulmamız için. Bu açının sağladığı şey şu. Bu açının trigonometriden, bu zaten trigonometriden geliyor. Bu açının tanjantı karşı dik kenar bölü komşu dik kenar. Karşı dik kenar burada AX olduğu için buraya yazıyoruz. Komşu dik kenarda AY olduğu için buraya alta yazıyoruz. Bunun arctanjantını alırsanız alfayı, yani bu açıyı bulmuş oluyorsunuz. Biz zaten AX ve AY'yi biliyoruz. Problem vermiş onları. O yüzden arctanjantını. Arctanjantı almamın sebebi şu açıyı bulmak. Şu açıyı bulmak. Bu açıyı bulduktan sonra da 36 dereceden 36.9'dan çıkaracaksın. Kosinüsünü alacaksın. Çünkü muhtemelen şu ivme vektörüyle şu radyal şey şöyle olacak. Yani bu ivme vektörü şu yönde olabilir. Bu A vektörü diyelim. Şu açıyı bilmem gerekiyor. Bu açıyı bilirsem bu ivme vektörünün radyal yönündeki bileşeni radyal ivmeyi verecek. Bunu biliyorum. Bunun büyüklüğü işte ax kare artı y karenin karekökü. Bunu kosinüs, şu açının kosinüsüne çarparsam bu açı da teta ile alfa arasındaki açının farkı olacak. Yani şu teta açısı, bu da alfa açısı ise bu ikisi arasındaki fark, onun kosinüsünü aldığın zaman radyal yöndeki şeyi bulacaksın o zaman. Nedir? İvmeyi. Well, this question needs some conceptual knowledge of vectors. You have to know how to deal with vectors. Okay? You have to know how to deal with vectors, some trigonometry, of course, and also physics. The radial acceleration is related to velocity and the radius, like through this equation. And then you're done. Okay. Next question is some guy also has some question, I guess. Okay. Let's save this. Let me put the last question over here. Right. This is the question, okay? A basketball player shoots toward a basket of 6.1 meter away in the horizontal direction, I guess. And the height is 3 meters. That's the position of basket. Basket is basket, yani topun gireceği şey, sepet. If the ball is released 1.5 above the floor and an angle of 60 degrees above the horizontal, what must be the initial speed if it were to go through the basket? So the best way is, of course, you have to draw the picture. So let's put the basket somewhere over here, and this is the basket, and the ball somewhere below of the basket line. This is the basket line, which is 3 meters above the horizontal. This is 3 meters. This is the point that ball is shot with an angle of 60 degrees with initial velocity v0. This is the angle 60 degrees. And it goes projectile motion and just enters to the basket. And from the point that the throw to the basket in the horizontal distance, it is given as what? 6.1 meters. Okay. So if you just take this is as the initial position of the ball, let's put the y-axis over here, and this is going to be x-axis. So this is our origin of the coordinate system, the origin. So y and x provides these equations. Y in, of course, projectile motion, y0 plus v0y times t minus 1/2 gt squared. Let's put the y0 v0 over here. And y, when it reaches the ball, when it reaches over here, the y is above the horizontal, 3 meters above the horizontal. That's the final point. This is 3. Y0 is the initial point of the basketball, which is 1.8 meters, is also given. 1.8, put over here. Plus V0y. This is V0 times sine of 60 degrees, sine 60, times t minus 1/2 9.8 t squared. Okay. So, well, you don't know what V0 and you don't know what time of flight is. But there is a second equation in the horizontal direction. In the horizontal direction, this is 0. Because the x is 0. X is 0 over, that means x is also 0 over here. X is equal to x0 plus v0 cosine 60 degrees times t, all right? Well, what are the parameters in this equation. X is from here to here, 6.1 meter, the final position in X. X0 initial position is 0, plus V0 times cosine 60 times T. Well, you don't know what V0, you don't know what T is, but you can solve for T in this equation. T is going to be just 6.1 divided by V0 times cosine 60. All right. So in the first equation, if you just put T over here, you get this equation. 3 is equal to 1.8 plus multiply this by T. T is 6.1 divided by V0 cosine 60, and V0s will cancel out. So you get tangent 60, right? Tangent 60, right? Times T. So no, V tangent 60, right? V0 YT, yeah. V0 YT, T is put over here, right? Tangent 60, because if you put T is equal to over here T, V0 is just V0 sine. Over here at the denominator you have V0 cosine. V0s will cancel out. Sine divided by cosine tangent time, yeah, tangent 60 over here. Minus 1/2 G times T squared, where 6.1 squared divided by V0 squared cosine square 60. And solve this equation for V0. Because in this equation, the only unknown is V0. And you can solve it, right? Over here, this is 6.1 squared. 6.1 squared. You have tangent 60 over here. You have 1.8 over here. You have 3 over here. These are just numbers. And cosine 60, you know, you can calculate. The only unknown is V0 squared. You can solve for V0. And that's the initial velocity of the basket. Initial speed. Okay. Okay. Is there any other problem? Any other question, problem you want me to solve? I think there are no further questions, so I will end the live session here. I hope you can do well tomorrow in the exam. I wish you success. So I will see you tomorrow, online. Not because you're going to take the exam by yourself.